Good evening, everyone. Welcome to the opening guest lecture of this year's workshop, part of our new MSc program in Computational Design and Digital Fabrication here at the University of Nicosia. The workshop has started yesterday. It will be hosted entirely online and will run for 2 weeks, ending on Friday, the 11th of December. Today, we have Odysseas with us for this first presentation. Odysseas is a computational design engineer and an adjunct faculty at the University of Nicosia, teaching computation and fabrication in the MSc course. He has graduated from the School of Civil Engineering at the National Technical University of Athens. After his studies, he joined Buro Happold to work as a structural engineer. During practice, he developed a special interest in complex architectural forms and their integration with structure, which he investigated through a series of projects. He joined the Digital Architectonics program at the University of Bath, from where he acquired his MPhil in computational geometry and structural optimization. He is currently researching interactive approaches to structural design and reinventing forms based on their structural performance. Odysseas is a co-founding member and director of Seamlexity, and today we anticipate that you will be showing some of his work in this lecture titled De-serializing Construction.
Okay, so I will talk about the work Seamlexity is doing. Seamlexity is computational design practice that me and Mihalis are part. Andreas is Andrea Menardo or Andrea or Andrea? And Andreas?
Yes.
Okay. Me, Mihalis, and Andreas are part of Seamlexity. So the company is based in Cyprus, and it was founded in 2016 in order to fill the gap of the digital design and construction in the local market. It now provides digital design services in a wide range of projects in the construction industry. Our portfolio ranges from very small projects, including decorative elements, sculptures, stairs, furniture, to large-scale buildings and high-rises where we apply BIM technologies. Despite our recent involvement in the market, we have been dealing with some of the most iconic buildings in Cyprus. We were mainly invited to collaborate in projects where these are characterized by complexity. Complexity is not purely geometrical, as you see in some of the projects, but our scope is to support designs from the concept to realization and de-skilling the complicated tasks. It's a pity that you won't be visiting Cyprus this semester, because last year we got the chance to visit the first two. Hopefully we get another chance in the future. So the title of my lecture today is De-serializing Construction. It's based on a similar topic which was discussed in a BIM conference a couple of years ago, where BIM, building information modeling, was idealized as the perfect solution for construction. But through my presentations there, I'll attempt to illustrate the human interaction to digital construction problems, as opposed to the trend of fully resolving issues through BIM software or automated construction skills using machine, and problems that could not be solved by any machine, at least not yet. So this video shows an idealized image of 3D printing of buildings. So while we have mastered the part of digital construction through CAD and CAM technology, we cannot yet talk about its complete digitization. And I will try through some examples to describe what exactly I mean with this. So this is a robot that probably saw today. I don't know if Christina took you to the robot room. It's a 7-axis robotic arm, and it's you can see it functioning, working on carving a sculpture. These machines, the 7-axis machines, they have great capabilities. They can construct any 3D model from physical materials by also automatically exchanging the set of tools. For those that don't know, the progression of Sagrada Familia is tremendously dependent on the use of these machines. Despite the possibilities of this machine, during the project, it was decided for a part of the work to be done manually, as this tends to be much faster and efficient and would have saved a large amount of robots' operational time. So here you can see the operator just breaking off pieces instead of digitally carving them off. So as a team, we were invited to design this project based on this parameter. So the models that we gave to the robot wasn't just the final 3D shape, but all the steps, including the manual labor that was input on this process. And here you can see the complete structure. It has a height of about 2 meters. It was geometrically optimized for against the parameters that was mentioned before, and also so that the material was minimized while its stability was maximized. Here's another building which was characterized by the construction specificity, which determined the information model that we had to assemble. It's the building's prismatic form had created great obstacles at the process of setting out the exterior shell. The resolution of these obstacles was the main information parameter which was used in our design. So the generation of horizontal sections in each of the building's discrete planes, which was the horizontal slabs, allowed for a traditional setting out process. And also the connection between these points in a single dimension or on a straight element created a variant of a conventional setting out method that defined the shell's geometry. So to explain it better, this is how it looked at the construction site before the erection of the formwork. So to be more clear, instead of trying to setting out the formwork in 3D from the exterior or the interior, which is a very difficult process and sometimes not that accurate, we combined these two methods by setting out the plan and the floor and the ceiling, and then connected these interconnected these dots in order to generate a puzzle-like structure for the formwork engineers to place the formwork against. And this is one of the images of the final project. This is the Oval Tower in Limassol. It's one of the landmarks in Cyprus, and it's characterized by its doubly curved geometry. This is the interior of the dome at the last floor. The last year students had the possibility to have a look at the interior of the dome. I don't know if it's accessible anymore because the owner has moved in and no visits are allowed anymore, unfortunately. We have worked with my team extensively on this project, and we're involved in most of the stages of its design and its construction. So inside the impressive image that I showed before, it's an even more impressive construction, which serves two main purposes. The first one is to bridge the opening of around to bridge the opening of approximately 30 meters between the main concrete structure of the building, and the second one is to carry the loads of the shell structure. During the course of construction, we realized that there was not an accurate setting out process to set out the framing of this dome, and mainly due to the limited visibility. So there was it was one of the tallest building at the time, and there was not an adequate number of surrounding buildings to place the setting on machinery in order to accurately set out this structure. At the time, even though the drone capture had fallen on the table, we didn't have such technology in Cyprus. But even if we did that, I don't believe that you can achieve such accurate results. So that meant that we had to redefine the shape of the dome consisting of flat elements, which would in turn form a new relative coordinate system that could be used for setting out the doubly curved geometry. Here you can see the scale of the dome. It was test mounted the fabrication factory in Greece. So the factory is 2.5 stories tall, and you can see it next to the factory. The plurality fact meant that the dome's framing need to have different rotations between each frame that could correspond to the flat panel. That was approximately 350 different ranges of angles, at which fittings needed to be designed and placed on the primary beams. And this is where we come to the term called interoperability, which was mentioned on the course before. We also had the geometry gym talk about interoperability, which is basically the exchange of information between the different software. As you can understand, each of the project's stakeholders were using different software platforms to design or fabricate different parts of the structure, which meant that all the data needed to be translated into data that could be read from different software. And here's a table that we generated for the data to be extracted to Tekla for the steel fabricator in order to rotate all the fittings according to the planar elements that we've shown before. And this image shows the inside of the dome shell. This is the tubes holding the skin, the secondary skin, the calzip type standing seam type roof. This needed to be placed in a very high accuracy, otherwise the roof system, the standing seam system, wouldn't be able to interlock together. So it required really high accuracy. But this is how the scaffolding looked from a close-up. This is how dense it was. And this is the image that you can see from one of the setting out stations in a nearby hotel. So you can see that it was extremely difficult for a surveying engineer to have a look in the interior and set out the secondary structure, even if we were using very new technology, robotic setting out machines as this one. Which meant that the only access that we had was internally. So the set out needed to be done internally. It was something that it was quite new to us. Typically, all the fabricators and the vendors of the system used machinery to set out the outer skin and give data back to the computer in order to generate their panel. But in this case, we had to find a solution to do this from the inside. So it was decided to take out the internal data of the shell and transfer these externally so that it can be projected perpendicularly off the skin to the secondary system by specific distances. And this is one of the tables showing specific data from each of the corrugations of the internal sheets towards the secondary system. And this is the only drawing that the workers had with them. So it's basically a table indicating the number of the corrugation, which of course was marked manually onto the corrugation sheet, and the distance which they had to travel perpendicularly in order to place the fitting for the doubly curved shell. And here we'll talk about construction logistics. It's a term that we're repeating quite a lot through the course. So in this case, again, this is the side view of the oval. How do you, for example, manage the construction and installation of 10,000 discrete panels in space? Here we use a combination of digital and conventional methods to place this. So since we've encountered all those setting out issues and difficulties and the visibility issues through the scaffolding, we said that the easiest way to do this is to place horizontal supports that will be parallel to the XY plane, which could be placed in a very traditional manner. All the contractors knew how to place horizontal fittings, and then digitally fabricate all the panels in order to have horizontal fittings and be hanged horizontal. So it's a combination of a traditional setting out method and digital fabrication. Which meant that we had to build a bespoke system, a parametric model to correspond to this design. So panelize the whole building and input these surveying the surveying of the horizontal beams in order to cut the holes on the beams. This, of course, was adjusted many times, so each of the setting out of the floors was different, and each of the holes were placed on the exact locations of the setting out. So this is a cutting layout for a set of panels that was digitally produced. And here's how the layout looks. Of course, the forming was done manually in a CNC press. So it's called CNC press, but basically it uses a force. It understands the type of material and applies specific force in order to bend the sheet at 90 degrees. But there's no automated way of doing so. So we had to design so that all the bends were the same. So even if all the panels were different, all the bends needed to be exactly the same. Which meant that the angles in the back had to be different. Here you can see, okay, the first one has to do with the grouping of each panels, and the right hand side image shows the different angles for all which was grouped, of course, in groups of specific tolerance, but they correspond to the fitting behind of the panel in order to be supported by a straight element. Which meant that since all of the panels were different, it meant that we needed a very clever way to mark this. All of the panels have a discrete marking on them, which is easily recognizable by both the fabricator and the installers. And of course, it can be understood by the maintenance guys in case anything needs to be changed. So this, for instance, means that we're at the dome, internal, south, east, second column, or second row, I don't remember, 22nd column. So I don't know if that was too fast, but I want to come back to the title that I gave to the presentation today. So de-serialization is, in computation, the process of constructing the object from the byte stream or the raw data. So how do we take this raw data and transform it into an object or another form of data that can be used effectively to aid the design purpose. This is one of my favorite images. It shows the heroes of the construction at the end of the day. So we have to always have in mind that these are the guys that will perform our design at the end of the day. So all the information that we hand out to them needs to be straightforward and clear, as they are the ones that they're in risk and danger at the end of the day. So that's all.